So this record we will continue on the programming in Octave for the structural analysis of truss. So the truss structure was uploaded in the class material already. Last time we prepared the input, right? So we transfer all the information we had from the coordinate of the nodal points. We construct the end map that tells the program how the structures connect, structural members, each individual member connects. And the E property, this is the property for each element. So we have the scale of the EA. In reality, if you analyze the real structure, then you just put the number in there. Like if the elastic modulus, for here it is the EA. You can just separate the E and the A, of course, right? So you can put the E in the unit which is consistent with the length unit, which is consistent with the area unit, because you cannot just do like the E being something maybe megapascal, and then the area is a square centimeters, and the length is in the other unit. All right, if you go with megapascal, force unit has to address that mega also. So better just clear out the kilo, mega, or milli. All right. So just bring it back to Newton, to meter. Okay. Don't keep the centi or milli over there. So cross section will be square meter. Length will be in meter. Area will be area in square meter. We talked about that already. The elastic modulus will be the unit of force over the length square in meter square unit. Right? So make sure that the unit is consistent. The program will not think for you. All these calculations is your hand program. So it doesn't incorporate things like that, and you get messed up when you receive the result, and you cannot track it that easily. The ALPH what alpha we calculate the alpha the coefficient of thermal expansion. Okay, right? Yeah, you see, just a few days I just got confused. What alpha? So coefficient of thermal expansion, because the alpha we also use it for the angle, for the orientation. So I was a little confused. And then we plot the structure. Well, by the way, this structure is undeformed. So undeformed shape. We come to geometrical properties. We verify the output we had last time. It looks like everything works properly, right? And okay, we wrote the geom to check in the last time. This piece of code is already uploaded. And well, by the end of this class, let's say today, I will upload the piece that is updated from last time. I will not replace the last time code, right? I just upload the newer version. So I put it in the separate folder. Now we are quite ready to start the operation, the real operation, because the former parts are just the administrations. Mostly you calculate this and that in order to prepare for the main piece of code. So you know that what you need in your system of equation, you have the K6, you have F6. Okay, K6 is the system stiffness matrix for all degree of freedom for equations, equilibrium equations from our DOF. So in order to determine how many degree of freedoms we have here, I think we identify over here we have the number of nodal points, and over there the next line is the number of structural element, right? Okay, so we come down here. First of all, cases will be allocated by 2 times NNDE. Because we are working on 2-dimensional space, we have just 2 displacement degree of freedom. We are talking about truss structure now. Later on, when we talk about frame structure in planar frame system, you have 3 DOF, X, Y, and rotation. So you're gonna allocate the space for 2 times NNDE. This is the matrix. This matrix will be enlarged later when we incorporate the degree of freedom for Lagrange multiplier, right? So you have additional row and columns coming in. Likewise, for F6, you will assign to be the 2 times NNDE, comma 1. Basically, if you want to have many forces, let's say in one structure, it might be subjected to many load cases. Then you have comma number of load cases, because if you construct the stiffness matrix already, for here very simple structure, we just let the computer code construct this K as many times as you want, because it doesn't take your time. It is just a fraction of a second. But in general, when we talk about the more advanced structural analysis, the structure gets like larger and larger. In one building, it will take time to construct the stiffness matrix, and that is the cost. So if you have many load cases, then you just construct K once, right? And then the load case will be used to solve by just keep changing the force vector, and then you inverse that stiffness matrix just one time. So that's up to you. It's up to the number of load case we have. The boundary condition, I will incorporate this later. For now, we can start with the main loop for I equals to 1 to NELE. What is going on here? You know that N4. You know that why is it just coming out like this? The N4 indent? No, not comment format. Indent code. Okay. So why is it? Let me check. I just understand something. Oh, okay. So this part here, when we conduct the direct stiffness structural analysis, we compute individual stiffness, and then we combine all individual stiffness and friction reaction force vector all together, right? So this is the procedure. So to do one by one element, we need the for loop from 1 to NELE. Okay. That means the I value represents the element number for now. So let's see. We can make a new function, all right? And we let this function name truss stiffness. Truss stiffness what we need in order to construct the truss stiffness, we need the EA, right? We need the length, we need the alpha, but well, we use the ALPH already, then we call it ORI, okay, orientation, okay. What else? EA, length, orientation. Well, that's gonna make the stiffness matrix, transformation, direction, cosine, that's all. Well, we can add it later, of course. Then the output from this function will be, sorry, the text is a little small, but okay. The output, I name it KELE, element stiffness matrix. So in here, I K log, okay, K local equals to 0 to 1 to 2. Local stiffness matrix, well, that is in local coordinate for the truss member. Then K log 1 equals K log 1 2 equal log 1 equal K log 2 equal 1.0 minus 1.0. Well, this is up to your style. You can put the EA over L minus EA over L. That's up to you, but I do it this way. K log equals to EA divided by length, right? Multiply by KLC. So the EA over L will scale to the 1 minus 1 minus 1 1. You get the element stiffness matrix for truss member in local coordinate. The next thing, we need the transformation matrix, right? So DCOS stands for, in my meaning, direction cosine. So this direction cosine dimension is 2 by 4, right? For truss. So DCOS something comma something equals to so we have row number 1 row number 1 2 row number 2 3 and row number 2 4. Start with what cosine value, right? I just don't want to go back to check in the very never memorized thing, I guess, huh? Cosine, huh? Cosine orientation and then sine ORIN and then cosine, no, not minus, this is not 0, this is 2 3 already. Other points are 0 because the matrix was pre-allocated to be all 0. So wherever is 0 we don't touch, just waste the resource. You can do it like this. You can say that this is equals to D cosine 1 2. Possible. Why is this going to be good to do this? Well, if the computer operations, if you compare between the calculation of cosine value and to obtain the value from that pre-calculated entry, it is easier to take the value from entry 11 and then equate it to the entry 23. All right, so it is faster. But if you don't like, you can just say that this is equal to, this is equals to cosine ORIN. Identical, this is the same. The meaning is the same, but when you do the programming, you also think about the computer operation, how to minimize the calculations in the computer. The thing is that doing the finite element analysis or direct stiffness analysis, that's a lot of loop. You have thousands of elements in there. That means operation like this, if you have the waste will be repeated 1,000 times. If you conduct nonlinear time history analysis, your stiffness matrix might be updated due to the effects from the nonlinearity. So softening is coming in, structure is nonlinear. You need to reevaluate your stiffness matrix. And as you reevaluate stiffness matrix, then you recalculate the K. If you do the linear time history analysis, linear means your structure is not changed. Then you repeat the K you obtain at the first step. But nonlinear time history analysis, this is a pain, because as it is nonlinear, then if you have 10,000 time step, you might need to recalculate 10,000 times. Takes so much time. All right. So if you have any waste anywhere, then your waste will be multiplied by thousands of times. And for each time step, in order to get the convergence, you might need to update your stiffness matrix for 4 or 5 times. So if you have 10,000 steps and then you have 5 iterations for one step, you're gonna have a bunch of calculations. And if the waste is there, a few points, then a few points multiplied by that many number of calculations is gonna waste your time. So you can be stingy a little bit with the coding. And that's the reason why I do it this way. Next, we need the KELE. Alright, the KELE is simply equal to the DCOS prime, which is the transpose. If you are not sure, come back here. If you are not sure, come back here and then assign some array 1, 2, 3. So then A prime, okay, this is a transpose. So D cosine transpose multiplied by K local multiplied by C D cosine, and that is it. So turns out the KELE will be the matrix, the 4 by 4 dimension. And we save it. So I'll save it. The name was TRSTIFF, Truss stiffness. TRSTIFF. Okay, save. Why is it frozen? Okay. It wasn't supposed to be frozen like that. This is Core i7 with like a bunch of RAM. That's something wrong with the window. Now, you are at this point, you can call, you want to get the stiffness matrix elements. KELE is equals to TRSTIFF, truss stiffness. First thing is the EA. Okay, what EA? How do you get EA? EA will be from EPRP matrix, right? So you go to EPRP and the which one, okay, which entry, which row to be taken from there. The row number is associated with the element number. So we go with I. So I stand for element, the I from here, right? This is the element that we are talking about currently, element number I. So you drop it in the I, right? And the column number 1, because the EA is in that first column in the EPRP. We're done with the EA value plug in. How about the length? The length was determined and stored in geom. The geometry here, well, a little small. Geometry here, so let's see. Geom I1 is the length, I2 is the orientation. So geom for the element I, right? The data structure for geom, the row is the element associated with the element number. Then the first column is the length, second column is the orientation angle 1, and geom I, 2. That's it. You get the KELE, which is pretty simple now. If you don't want to store the value in the geom, if you think this is the waste of time, then you can put this piece of the code in here, and then you run the calculation for the length inside this loop. That is also fine because the number of operation is actually identical, NELE operations, right? But doing this way, it is just easy for you to understand because, okay, I calculate the length first and then next step. But I might just compute the del X, del Y, and then do all of this, and then get the angle and the length just over here. But okay, inside this loop, things seems to be much smaller, not as complicated. You get KELE. The thing is that your KELE right now, it is the 4x4 matrix. This 4x4 matrix should be plugged in to the system matrix. How to plug in? You have in total 16 entries to plug in. Okay, so out of these 16, the operation will be done actually. If you think about the number in the row and in the column, the first two rows and first two columns are associated with your first node. So let's see. If we look at the member number 4, let me see if I can zoom. Oh, yeah, I can do it. Okay, all right, then easier for you. Okay, more friendly to you. So sorry about the beginning part then. But if you look in the YouTube, then you'll be able to see. So you look at the element number 4. The first two entries, first two row and columns are for the DOF 3 and 4. Right? 3 come from 2 multiplied by 2 minus 1, and 4 is just 2 multiplied by 2. So first two row, first two columns are for 3, 4, and then the next node number 3, the associated degree of freedoms are 5 and 6. So this one is quite simple. It's not tricky at all. When you plug in the element stiffness matrix to your system, you just bring the 3, 4, 5, 6. You just bring this matrix and add it into the entries for row 3, 4, 5, 6. So it is just connecting, right? It is like a one big piece of 4 by 4 stamp on the cases. This is just a simple case where you have the element number just 2 and 3 continuous like this. But if we are more realistic, okay, life is generally not that simple, so this situation always occur. Sometimes 4, 7, or even like this, like 6, 4, okay. For the 4, 7, the node number 7, DOF number 7, 8 will be at the first 2 row and columns. And for the number 7, it's going to make the 13 and 14. So you can imagine that things in the 4 by 4 matrix has to go to the right place in the cases that will be programmed. Or the case like this is a case that we generally don't like. You have the larger node number there for the starting node, and the ending node we go with the smaller number. So that means the first 2 columns and row are 13, 14, and then you come back to 3, 4, right? It switch around. But it doesn't really matter. The computer just take care of this. Or when you do hand calculation, you just follow this, just drop in the entries to the right destination. That's the whole idea. So now the operation will be row wise and column wise. Okay, the plugging in, you will scan the entire row and then you come down row by row. So column 1, column 2, column 3, column 4 done, and then you come down to the next row, plug in column 1, 2, 3, 4 to the next row, and so on. As the operation will be pretty much like the loop, okay? It is repeating. Then we're gonna use the loop, for loop, to conduct this plugging in. You don't see the benefit so much in here because this is just a truss structure. The plug-in operations actually doesn't take you so much time. But if you imagine you go with some other kind of structural element like the plate bending, you might end up with 12 by 12 degree of freedom, 12 by 12 matrix. 12 by 12 matrix, 144, right? You cannot write a code 144 line in order to just take care of one element. It is not a good idea. Okay, well, so let's see how the operation will look like. Well, we're gonna need the for loop, of course, but you cannot use the I anymore. Now it's gonna be the for j, okay? I will be out there, j equals to 1 to 2. Why is it just 1 to 2? Why is it not just 1 to 4? It is 1 to 2 because you have 2 nodes for each element, and 1 node means 2 degree of freedom. So basically, if you break down your stiffness for a truss member, you will break down the 4 by 4 matrix into 4 zones. The first zone's element, the entry 1 1, 1 2, 2 1, 2 2, okay, a group of 4. So this is associated with node number 1 and node number 1, okay, in both row and column. Next, you move to the right. So you go to entries 1 3 1 4 2 3 2 4 associated with node number 1 and node number 2. Okay, DOF from node number 2 and then the false DOF for the node number 1. Move to the next group, come below row number 3, column number 1 and number 2, row number 4, column number 1 and number 2. All right, this is node 1 and node 2 and 1. Okay, DOF 1 and the last one 2 2. So it was 2 3 3 3 3 4 and 4 3 4 4 entries. Okay, so we break this down into 2 groups, and then the number 3 will be calculated from, you take the node number multiplied by 2 minus 1. So this is the overview. So I have 2 for like this, because you're gonna move in a column direction and you finish one row and then you come to the next row. The operation will be, the plugging in operation, you add the number on top of the existing number. Okay, keep in mind, in the program, if you say that cases is equals to maybe KELE something, so the number will be replaced, all right, in the programming. So you cannot just do that. You have to say that it is a cases and add up with KELE. The thing is that now we need to identify which entries that we are going to add up. So we need to identify the right location. Cases of what? So you think about one block, all right, one block. In this block, let the K control the column and J control the row. So you have 2 times J minus 1, comma 2 times K minus 1. So this is equivalent to the entry 1 1 if you look at the first block, entry 1 3 if you look at the second block, entry 3 1 for the third block, and entry 3 3 for the fourth block. Okay, because the K value for the first block is 1, J value is 1, so first block you get 1 1. All right, second block you drop in the K value equals to 2, but J is still equals to 1, so you get the 1 3 because the J is 1, and so on so forth. You just run that calculation. So these values, so we are talking about the same point, right? So the new value of cases is going to be the existing value of cases add up with the value in KELE. Oh, one second. I did mistake. Okay, this was supposed to be the location in KELE, not the cases. For cases, it is not just J and K, because in the cases we need to take the node number from here, right, from Nmap. So let me let me start this way. S num and E num. Okay, starting node number and ending node number. So starting node number is, I think S num is too long. Okay, just go with S and E. So S is Nmap of element I that we are talking about, and comma 1, starting node. and end map I comma 2 as the ending node. If you want, you can just replace, you can just take this end map I1, end map I2 and put it in here, but the line will be just quite long, so I think it is easier to do it this way. Starting node, ending node. Okay, so let's look at this together. Let's just assume that we are working on this element number 5. So the S is 4, E is 7. Wait. J is 1, 2. No. Not that simple. Sorry. Try to simplify, but we're gonna keep the end map. Okay. No, not that. One moment. Should I just it was supposed to be I, J, and okay, that wouldn't work. I, K. Okay, clear this out. Will not work. Architecture is not that beautiful. This one will be the best. Okay, let me explain. 2 times end map I, of course we are talking element I, and J. First of all, J control the row. Okay, this is the row. So the J row is associated with the node number. So the first node number will be 4. First node number is what? Yeah, first node number is 4, second node number is 7. So you will first start with dropping in the number 4 in here. So J ranges from 1 to 2. Okay, end map here will, if J is equal to 1, then end map IJ is equals to number 4, node number 4. When the J ranges as it is in this loop, so it will range from 1 to 2, then you will end up with end map this whole thing being 7, right? You're gonna obtain the value, so the number 2 will bring you to the second, okay, node. And then for the second node you have 2 DOF. The first DOF you got to -1. The second DOF you got to you don't have to -1. Okay, but now we are talking about one block, so we're gonna start with the -1 and -1, and then row -1 and column without -1, and then come down to row without -1, column with -1. Well, you will see. I will just copy this. I just want to make it like this. Okay. Okay. This I give you a comment a little bit. This shall be like entry 1 in the block. Next one will be the entry 1 2 in your block. What is the block? I think I should just visualize you a little bit about what I said about this block thing. So drawing it in Excel here. So in your stiffness matrix for the E F G H I J K L M N O P so I merge and I merge and I merge and merge. This is a starting node. This is the ending node, right? This is the starting and this is the ending. Just try to help you visualize the matter. Oops. So this starting, you have the 2 times starting node minus 1 and 2 times starting node, 2 times ending node minus 1 and 2 times ending node. So here is the DOF, right? Here is the node number. Same for here and for here. And the block I mentioned is just like this. Okay. So the operation we had the for j equals to 1 to 2, and then it is the thing that is nested inside is the k equals to 1 to 2, and then I can just copy this thing and put it here. Okay. So first, this one, the 1 1 means the 1 1 of each of these. Okay. When you come down to the each individual block, this is 1 1, this is 1 2, this is 2 1 and 2 2. So this is for each individual block. You have flow blocks. In each block, you need to write the code to take care of the plugging in of each of these. Right. So let's take a look. The first one, cases. Okay, this is the location in cases. The location in your local is just column 1, column 2, column 3, column 4. So it is here, right? KELE 2J, because the J will vary from 1 to 2. Okay, so 2J minus 1, 2K minus 1. If you talk about the J being 1 and K being 1, that means you are in the first block. Oops, sorry. Yeah, you are in the first block. That's correct. J equals to 1 and K equals to 1. Yeah. I think I can add more columns here, and then I can. You will see the S. I will say that N map. I1. Is it easier for you to Is it going to be easier for you to understand? Oh, but I said S and E there. All right. I can just do it this way. Maybe sometimes it is unnecessary. Too many informations. S and E. Okay. So this is for this one. 1. N map I. Okay, we don't care about I. You care about J. So J start from 1. Okay. J start from 1. J start from 1, and the K is also for 1. J controls the row operation. So J, you start with this row, and then K will range from 1 to 2. So you move to the next block, the block green, and then you finish the loop K. All right. So you come out, then the J will change from 1 to 2. So you come down to the third block, and then the K change from 1 to 2, then you go to the fourth block like this. But inside each block you have 4 entries. So in each entry, okay, you have this one, which is 2J minus wait. Yeah, the row is controlled by J, and then the column is controlled by K. So we come to here. This is the K without minus 1. Without minus 1. And also here without minus 1. Alright. Copy and come down to here. We move to the entry 2-1. To get the 2-1, then you clear the minus 1, which is associated with the J, right? To J. And last one, and this for 2-2. Okay, we can just check over here. So give it a try. let me copy the Nmap and put it in Microsoft Excel. So it will be on just your side and try it one at a time. So element number 5, 4, 7. 4, 7. You come to here. First one, when j equals to 1 and k is equal to 1. Okay, the first case, j equals to 1, k equals to 1. You drop in Nmap j equals to 1, k equals to 1. So you put in the Nmap ij is equal to 4, and also Nmap ik is equal to 4. Alright, you drop in the number 4 in here and in here. So you start with this group. In the cases, you are talking the element, the entry number 4 times 2, you get 8 minus 1, you get 7, and 7 because, okay, so this entry will go to 7, 7. What is it? It is from KELE. J equals to 1 and k equals to 1, so it is the 1, 1 in KELE. Next, you are talking about cases. So Nmap ij is still 4 multiplied by 2 minus 1, you get 7. Nmap ik multiplied by 2 without minus 1, you get 8. How about this one? You have KELE 1, comma, k is 2, right? K is 1, so you get 1 multiplied by 2. What else? What next? Cases. So Nmap ij is equals to 4 multiplied by 2, you get 8. Nmap ik multiplied by 2, 8, and then minus 1, so you get 8, 7. And this is KELE. What? 2 and 1. Now cases 2 multiplied by 4 and 2 multiplied by 4, 8, comma 8 is equals is added by the KELE 2, comma 2. Right. Look hectic, but here will be easier to understand. I have no idea how many nodes. 7 nodes, right? 7? Yeah, 7 nodes. So you have just 14 DOF initially, F1 to F14. You make the matrix. So actually we used to do this by hand. Now you get the stiffness matrix of element number 5. Here is what Okay. When you get stiffness matrix for element number 5, you will have this 4 by 4. So this 4 by 4 will be coming into here 14 by 14. So CLASS18 is getting the 1 1. Okay. CLASS18 is getting the 1 1. So 1 1 is the A, right? 1 2 is the B. 1 2 1 is the E, and 2 2 is the F. So let me drop it in. 7 7, get the A in. 7 and 8, right? Here you get the B, and then 8 7 you get the E, and 8 8 you get the F. Okay, now it is plugged in for this zone. So we move to the next zone. The next zone, dj is equal to 1 still, right? Because our loop, the j loop is outside and the k loop is inside, so it's gonna finish the k loop, and then okay, the index in the k in the j loop the index in the j loop will change. So 1 1, and then the j equals to 1 and the k equals to 2. So this is going to change. So this is 4 still, and the second one is 7. That's gonna make the cases. Look at this together. 4 will be here, so I get 7. 7 will be here with the k, so you get 14 minus 1, right? 13. What is this KELE? J is 1, so you get 1. K is 2, you get 3. Right? You take the k equals to 2, plug in here. 2 times 2, you get 4 minus 1, you get 3 then. KELE 1 3, what is it? This is a KELE. You have 1 3, it is the C. Next, for the cases, still 7, 14, right? 4 come to here, 8 minus 1, 7 come to here, multiply by 2 without minus 1, you get 7 14. This is KELE. What? 1 2 1 4, right? It is 1 and 2. 1 is here, j equals to 1 multiplied by 2 minus 1. And then for a k equals to 2, then you get 1 4. 1 4 is D. Next, cases of the j equals to 1. Okay, you get the 4. You take the 4 multiplied by 2, you get the 8, and then 13. And KELE, what? 2, 3, right? 2 3. Okay, don't forget the j equals to 1, multiply, you get 2, k equals to 2, you get 3. 2, 3 is a G. K6 this time 8, 14 and KELE 2, 4, which is the H. Okay. So the C will be plugged into 713. 713, you get this C. The D plugged to 714, this one. And then G and then H. Okay. Just like your operation by hand, and your brain is actually processing this information, but you just cannot formulate the operations in the brain into the line by line algorithm. Here is how we convert it, and that's the programmer job, right? Next one. I just copy this whole thing and paste there. So you finish the loop K, then your J is going to update and the K will restart. So the end map here turns out to be 7 and this one here turns out to be 4. Okay, the J come back to 1, the K come back to 1 and the J goes to 2. So K6, you plug this 7 in here, you get 13. You plug the 4 in here, you get 7. 13, 7. How about the KELE? The KELE 2 and 1, right? 3 and 1. Back to these cases. Still you get 13 and you get 8. The KELE you get 3 and 2. 3 and 2 is this one, J. These cases, seven come in here, turns out to be 14, and 4 come in here, turns out to be 7. KELE 2, right? 2 in here, you get 4 and K is equals to 1 and 4, 1 is the M here. 2 cases 14, 8 and KELE 4, 2 N. So here is what you will get: 13, 7, 13 row 13 and 7, 13, 7 I, and the J is 13, 8 and M and N. And the last group, so I just need to show you just once for one element, and if you are convinced the other elements are going to work in the same way. So for now you have 7 and 7, right? So first one is a 13 and 13, and here is going to be 3 and 3, right? 3 and 3 is the K. Cases, the next one is 13, 14, KLE 3 and 4, which is the L. The next case is 14, 13, KELE 4 and 3. 4 and 3 is the O, and 14, 14. Actually it is P, so 4 and 4. K, L and OP. There it is. Just that. So the operation that is programmed under this code work this way, in the way that you want, same as the manual operation. Come back to Octave. Why isn't it just give the automatic? Okay, indent. Right. And N for the last one. What else can we do? The next step is about the load, actually the fix and reaction. But for the truss problem, generally nobody apply the load on the span of the member. Most of the time the load is applied at the nodal point. So for truss structure, you will not see the necessity to do the fix and reaction assembly. But for the frame, the procedures will be somewhere inside the J loop. It doesn't need to the K loop because the operation of the assembly will be just one-dimensional assembly, right? It is not the matrix, it is just one-dimensional array. So it needs only one loop to assemble that fix and reactions from individual element to the system fix and reaction. Then now we have the stiffness matrix. We will talk about the boundary condition. So the boundary condition is going to be given boundary conditions, to be precise, essential boundary conditions. So we need to provide I will make it N, B, C, N. Okay. Number of boundary conditions. The structure this truss structure, we have the 3 displacement boundary condition. The left support was subjected to the restraint in the X and Y, and the right support is prevented against the vertical displacement. So in total there are 3 boundary conditions. Number of essential boundary conditions. Okay, we come down here. Well, that's up to you. I mean, how to set up the architecture for the number of boundary for the boundary condition. I think I'm gonna use the Lagrange multiplier, so that's gonna make your matrix bigger. The point is that if I use Lagrange multiplier, I have a freedom. I can do it, not only just fix it as a boundary condition. We can apply the displacement if we want. Alright, so this one here, I will make the boundary condition the code doesn't need to be that fully automatic. Well, actually, if I write my code, I will just drop in the node number, and then I will enforce the X boundary condition or Y boundary condition at the given node number. But well, over here we can do a little calculation. We don't need to, as you know, this is not going to be the code that you sell. So the data structure, we're gonna need to input the matrix that you have the DOF number and the DELTA, the delta, which is the prescribed displacement magnitude. You don't need to put the negative sign in front of delta. Okay, the algorithm, the rest of it will take care of that negative sign. But if you have negative displacement, you need to put that in, right? Settlement downward against the direction of y, that thing you need to put. So what should be the name? BCN okay. Yeah, okay. Just I move this one down there. Or actually that line might not be necessary. I'll just do it. By just taking the size. Oh, frozen again. Size of A. Let's see. 1 and 3. Okay. So the first is the number of row and the 3 is number of column. And the data structure will be B, C, and D, comma 1. So here is your B, C, and D. First of all, the degree of freedom number 1 is to be restrained, and the displacement for that degree of freedom is equal to 0.0. The second, at the same node number 1, the Y degree of freedom is restrained. So this is the DOF number 2, and you get 0.0. And the last one, the node number 3, which is the right support, the degree of freedom that is restrained is the vertical degree of freedom. So that is number 4. 0.0. Close the bracket. This. I just say BC number 3 BC number 2, BC number 1. Oh, thank you. Yeah. Die. Now we have the boundary condition. We have no force yet. So actually we can run just a simple structure under the force. So here will be the apply nodal forces. Name it apply nodal forces, but actually it is applied at the DOF. DFRC, okay, equal to, you put the DOF number, so just make sure that you know that the data structure, you record it a little bit, DOF number and the force magnitude. You need to put the minus or plus in order to account for the sign, the direction of the force. And well, if you look back into the truss, the sketch of the truss, first of all, I think we can just start with a very simple apply load. We shall apply the gravity load downward at the node number 5, 4, and 2. The node number 5, the DOF is 10. And if I apply some sort of gravity load, it is going to be the minus, I put some number 10 as the load magnitude. The next node will be number 4, so the DOF is number 8. We have the same load, so this problem will be symmetric. The third, node number 2. Node number 2, you get DOF number 4, and then that is minus 10.0. And NFRC, number of forces that we have is actually equals to size of the FRC comma 1. So F6 actually we can move it there. So we allocate the array for F6, and for I equal to 1 to NFRC, we have to go to F6, which entry? The entry is equals to DFRC I comma 1, right? We are putting the DOF number in the first column, so you can just go directly DFRC I column I comma 1 comma 1, because the F6 is a one column array, and the fsys is equals to fsys itself plus dfrc I comma 2, which is the force magnitude. Apply, and that's it. So this will bring all the forces into your system force vector. Actually, if you don't want to write a piece of code, then you can write the fsys being the 14 by 1, and then you just drop in the minus 10 at the row number 10, row number 8, and row number 4. It could be done that way, but I just try to generalize it, so maybe this one might work better, or might be easier. Now we talk about the boundary condition. The boundary condition will come after here at this point. That is going to affect your fsys and your ksys. How does it affect? It's gonna add the row and column to this original matrix and well, let's say original array. But let's see how to add the row and column to your now. Okay, help is here, documentation on this. Let's see, search how to add row storage of sparse matrix and array. Loading and saving image. Cannot find. Maybe just try. What if A? One second, let me think of it. Okay, you have two things in there. Okay, in A what one and this. No, A1. Let me check. Oh. Resize wrong. Magic colon. I just don't remember this. Do I have the internet? Add to Rome. Okay. Documentation on this. Okay. Or maybe just go ahead with the Google. Add row array. Matlab and Octave use the same. Append, okay, row at the end of matrix. How can I add row to matrix? Okay, just look for a few. Concatenating, right? This black tab just obstruct. Where append specialized matrix function. Expanding the matrix. You can expand the size by inserting a new matrix outside of the existing index. Okay, so 4, 5. A is 3 by 4, and then what? 4, 5. 3 by 4. So 4, 5 come here, and 5, 6 in these two. To expand the size of the matrix repeatedly, such as within for loop. Okay, I don't need to do that. Empty array. Well. Can also expand the size by inserting the new matrix. Okay, this is one way that I don't like. I can do it that way for here. I think this one. A is equal to 1 and hey, what is A? Make it like this. Okay, so you add the row in there. Okay, insert the row in there. So 1. Yeah. A. 1, 3. One, two, or what is that? 1, 2. A1, A3, A2. Just go ahead with this one. We can add 4. Okay. Modification of the original system arrays for BC. Okay, so I'll just go with this one. Easy, but I just don't like it. 4, 5 and 5 to 6. Okay, so we just need to put the we need to just push the limit to this corner, right? Let me check again. F sys and K sys. K sys for time being we have the 2 times NDOF and NDE. And okay, 4, 5. Okay. 4, 5. That is equals to NNDE plus 1, and then NNDE plus NBCN. NBCN, yes. And then comma. Yeah. So this is supposed to work. equals to the matrix with the we got to let's see zeros NBCN comma NBCN. So I need to try, well, check it first. Assign the array. A is assigned to be 1, 2, 1, 3, 3, and 2, 3, 4. And then A, well, let's see. B is equals to 3. So I will say A 2 plus 1 and 2 plus B. I just need to check if this is going to work. Zeros B comma B. Yeah, okay, works. So this line is going to work. Likewise,
So what is NBCN?
number of boundary condition.
So can you go?
Oh yes.
So there size D Farsi comma one. What's that one?
What is the comma one?
N
Oh.
Farsi size line number 94.
94 NFRC. This is force.
Size D Farsi comma one.
DFRC is this one here. This is the degree of freedom force. The command size. I showed you size. It returns you the matrix. The first one is the number of row. Second one is number of column. So the argument here, size A comma 1, you're gonna get the 5. Number 2, you get the column. So for the F6, there is a command that is used to insert just in between. This is just on the right and rightmost and belowmost rows and column. But I used to use another command that can insert the row and column just in between. Don't remember, just need to look up. Well, if you spend a little more time just searching further, then you will find. For this one here, comma 1 equals to zeros. We add just what? We add just the row, right? Comma 1, we'll see. I think I need to check this one. NBCN. So let's check this one here. It works for this 2D array. How about 1D array? How do I? C is equal to 1, 2, 3. 1D array. Then I will say C of I need to add the 3 plus 1 and what? B comma 1 equals to zeros. 3 1 non-conformal. So should it be 1 3? But it doesn't make any sense. No, non-conformal. Argument option 1 0. This is going to increase the, well, it's gonna push the diagonal corner, but how to push it out just in one dimension? Yeah, that's why I don't like this. It works for this one here, but for one dimensional array it doesn't make any sense. Concatenating append row. Let me see. Hi. 3 by 3. Okay. And you're gonna add in there. Alright. Yeah. Oh, rep map. I think it's too complicated. That must be better. Okay, A is like this, so A is equals to A. Yeah, this one is better. Yes. So we append this. Row number 1, column 1 to 3. Okay. We append A. So that's gonna make 1 2 3, and this is just 1, and then append the number 0 in there at the back. Okay. Let me try. So C is equals to C. What kind of bracket? Yeah, the square bracket. So C square bracket, and C square bracket. Where is it? And square bracket there and C inside, and then we need the C in the column 1, in the row 1 2 3, the first column, and then we append it by zeros, maybe 3 1. Yes. Okay, great. Yeah. So F6 is going to equal to F6 equals to this one, which is the F6 itself. Do I need to say anything about it? And this okay, let me try if I can make it more concise. So I can say just it is just a C and then append this. Yeah, alright, yeah, this works. So I don't need to talk too much. F6 and then zeros. How many more rows we need? N, B, C, N, right? Comma 1, and that's it. We add the row, okay, in there. So this one here, I just change. I can append the row. So this append the row. Can I append the column? This, okay, this add more row. Okay. This is not how we add column. Do you get the point? when you put this semicolon, then it comes down to the next row. So this add more row. But how to add more column then? A equals to okay, this is going to just add more row. How to add column array Matlab? Yeah. How do I add column to the matrix? I create something like that. Okay. Oh, right. Delete first column for what? New column, random, something like that. Add new column. ARR is something. And then you delete it. You make a new column. Oh, okay. All right. So add new column, you just put it this way side by side. Okay, great. Easy. So start, first of all, I think we start with the row adding and then column adding. Or yeah, vice versa. It's gonna work. Cases, we add row first, so zeros, number of row, right? NBCN, and then column. Number of column we have right now is 2 times NNDE. So the dimension has to be the same as original for the number of column. And then cases is equals to cases and zeros, 2 times NNDE. Wait, how many? Okay. Yes, plus NBCN and comma NBCN. There you go. Or now you add number of rows in there in this line, right? Add row. So the dimension has changed into the 2 times NNDE plus NBCN. This is the new dimension, number of rows you have. So you need to add zeros, of which the number of rows is equal to 2 NNDE plus NBCN. And then how many columns do you need to add? You need to add NBCN columns, right? That's it. Basically, you can do it in the other way around, like you just reallocate the zero matrix, of which the size is 2 times NNDE plus NBCN, comma 2 times NNDE plus NBCN. And then you copy the cases and F's. Okay, you copy the cases into this matrix at the upper corner, and then you have the remaining rows and columns are just filled with zero. That could be one way. The point is that the reason why I don't do that, because you have one big matrix. In reality, you have one big matrix, and then you are about to allocate another big matrix, even though it is just a zero everywhere matrix, but still it takes a lot of storage. Zero takes the same storage as non-zero. Okay, that depends on the bits that you allocate. So you duplicate the size approximately about 2 times of this storage you need. That means if the problem is big, then doing it this way I show, and doing it by reallocating another array, that simple technique is gonna reduce the size of the possible problem that you can analyze by just 2.5. of this technique we are doing here, approximately a half, because you have constant size of the RAM. So if your RAM say 100, then you can have 50 and 50. That makes the problem, the capability of analysis smaller. Right, and then you need to plug in the -1. So if we think of the how could I say, if we think of the boundary condition like one structural member, so in one boundary condition,
so here we need to consider the different axial rigidity.
Different axial rigidity where?
The top one you put the
Well, that is already taken care of because the code is enable this thing. 1, 3, 3. So in the calculation took this EPRP, right? EPRP, is in there, all right? But the point is that, now for the boundary condition, you're gonna have the -1 and -1, 0 and 0. This locate somewhere for this problem. I will do it this way. So numerically, you can look at the boundary condition like a member. Well, like a member with this stiffness matrix, because you're gonna plug in all this into the whole system matrix. So what is it? How is it going to be? First of all, for the first degree of freedom, I think we have the number 1, right? Degree of freedom number 1 as a restraint. The support is there. So for the number 1, it's gonna come to this point. The F1 will be moved to the unknown vector. F1 will be moved to here. That is going to 0 this one. Alright. This is the operation that will occur when you take care of the boundary condition. F1 is moved down here. And since the F1 is moved, you leave the -1 there. And you say that here is the minus delta. Let's say delta minus delta. So if you look at this as this is minus delta and this is -1. So if you look at this like a member, this member has this operation. Okay, it is associated with these two, and you have this, and this. So it's gonna add so it is going to add these numbers to the matrix. It's gonna zero this one. If there is anything, then it is going to be 0 first, because it will be replaced by the F1 over here. This is minus delta displacement. Over here we prescribe it to be 0, but I just generalize it. Zero this out, put the minus delta in here, put the minus 1 in the row associated with F1 and column associated with U1. U1 is the DOF that you prescribed in here, right? This is the DOF. Okay, so quite a bunch of things flying now. Let's code it up. I have the for loop again from I equals to 1 to NBCN. So the operation, we are going to zero this one here inside the F6. F6, what is the entry? The entry is the BCND, all right, for the I boundary condition, comma, number 1, which is the DOF number, comma 1, because F6 is just 1D array, and that is equal to 0. So I do this. Done. Next, I need to put the minus delta. F6, where you have the 2 times NNDE plus I. Come down here, right? This is 2 times NNDE. Total degree of freedom we have. Plus I. Now we are talking about the first boundary condition. So you plus 1. Next boundary condition you will come to here. And next. Okay. Comma what? Again, comma 1 is equals to minus what? BCND of I, comma 2. BCND I, comma 2 is this column. This is the this column. This is the prescribed displacement. If you say 0.0, you get the support. You are done with this vector. You move to this one. So for a 0, you don't have anything modified in here in your stiffness matrix. We don't make any modification. So we don't touch this one. We don't touch this one because this one is this corner. Nothing to do. So you just need to put the minus 1. So the first minus 1 easy because this is the column of DOF you enforce. But how about the row? The row is the same row as the minus DEL. So K6 of, we need the row number first, right? The row number is this one. And column number is BCND I, comma 1 equals to minus 1.0. How about the next one? This one here, the column number is the same as the row number of of this one, and the row number is equals to the degree of freedom number. So I switch N4. Almost. Enforced boundary condition. We have the false vector already. Well, I'm pretty sure the first run is gonna hit the bug. Of course, you got to find it out. But this is the best that we can come up with base. But we are very careful about it already. The last one is the solution. You need to find the displacement solution and also the force reaction. Well, for this problem, you're gonna ahead of time that the reaction force should be 15 and 15 onward, right? Because you have in total 30 applied downward, and it's gonna be 15, 15. The point is that let us check the linear solver for the Octave. I just always use Matlab, and the solver linear solver Octave. I just need the function, the syntax. Linear programming, no. Solving linear system of equation. Okay, yeah, and then what do we have? What? Inverse matrix. It is slow. LU solver. Okay, I don't do it. LU solver Octave. Function LU Octave for sort forge. Okay, we get the L, we get the U, and then compute the LU decomposition from LaPack. A is a full, then subroutine from LaPack. If A is sparse, then use the U MPack. Whoa! It can. The result is returned in the permuted form, where we get the A matrix. You do the LU, you get the lower, the upper, and the P. Okay, the matrix is not required to be square. Alright. Typically I just need the final result. I don't need to do the LU in between. Okay, given the string argument vector LU returns a value PQ and vector value such as a full matrix is equal to L. I think there must be something. Matrix factorization, general LU decomposition. I don't just need decomposition, I need it solved. Okay, L and U. Okay, we go multiply L and U. You get 147,258. Okay, you get upper and lower, and I need a solution. Matrix factorization as well for solving. Yeah, this is good. A and B, great. And then we solve. Oh, it's just A over B. You just do the A over B? Seriously? Solving CD. Okay, just divide it. But this is going to take the. Why do we need the LU solver? We don't want to inverse the matrix. We try to go for the solver that is better than just taking the force vector multiplied by the inverse matrix of the stiffness matrix because the inversion is expensive. Eigenvalue problem, LU decomposition. Okay, we have the L value, the P permutation. Fine. I just get it first now. So displacement is equals to F sys this backslash, right? I saw the sort of backslash alert for divide into okay. Matrix of is A or B in Octave is A inverse times B in mathematics. Okay, so A will be inverse, right? A will be inverse, so A will start, so K sys and then backslash and B. K sys backslash and F sys. Control save. Then we do the main. We call it 15 and 15. Okay, so at least I think this is good. We are good. I think we are correct. 54. I just wish I have more time to do something a little bit. We can plot. I thought that we're gonna get the bug and then correct the bug for a while until we get the solution. Such a fluke programming without bug. Plot deform shape. So I go there for the plot. Temp x, temp y. Okay. So I come here. I just brought the code for the plot. And then it will just take more time. I just need to run to that room in a few minutes. So we have the undeformed shape plot already. Here we are going to plot the deformed shape, and that is we are about to finish. So this one on the top is an undeformed, and then we compare with the deformed EXAG. Exaggeration factor will be for if you use SAP, and once you analyze, you can adjust the exaggeration factor, because the analysis you get very small deformation like 1 millimeters, and then you show the deformed shape, you don't see anything. So you exaggerate the displacement to enable you to see the deformed shape, so it is exaggerated. Here we do the same thing. So the exaggeration factor, multiply by the displacement, right? Add up with the original degree of freedom or original coordinate of that nodal point. So original coordinate is given by xy co. And how about the displacement DISP? Which displacement that you take? It is the displacement that come from what? Or the screen. The screen. Oh, okay. The picture is not. Go watch YouTube. we are about to finish, so maybe I don't spend time fixing it. The displacement, how do you take the displacement? Displacement, you come up with a one-dimensional array of displacement. So we need to pick the displacement that is associated with the node, starting node and ending node. All right. So we take the end map I1 we have over there, but as it is the displacement, you need to make it degree of freedom. So end map I1 gives you the node number, you multiply by 2 and minus 1, you get displacement in the x-axis. So we add the displacement in the x-axis to the x coordinate. I'm gonna just get this done real quick. I need to run, but I think we shouldn't just leave it here without seeing the deformed shape. I think we are approaching to the highlight. Exaggeration and displacement for the y coordinate, right? Without minus 1 starting node and comma 2, okay, for ending node. Okay, x and y we have all, we exaggerate, we just use the dotted line, or maybe we use a solid line and red, and the original structure is a dotted line. Okay, hope it works. Save and run again. Oops, nothing. No. Just that? What? Didn't hold on or what? Okay. Home. Hold on. Save it. And call it again. Yeah! Okay. You can come and look at my screen. So the dotted line gives us the undeformed truss. We apply the vertical load at this point, and this point, of which the magnitudes are all equal to 10. 10 down, 10 down, 10 down. We saw that the reaction forces are 15 and 15. Equilibrium wise, it is correct. And now you can see the deformed shape, and deformed shape looks great. Okay, so this code actually works. Now it will be uploaded. You can get this, modify, play, make a new truss structures. Million possibilities you can do. In fact, if you do not have structural analysis program, expensive one, SAP, it has Stat Pro, and you want to do just a roof truss, which is a planar truss structural analysis, then just use this, and you get all reactions, plots everything out. It is not beyond your capacity. The structural analysis program is just this that we sit down and develop for 2 classes, and not what is more complicated is just the graphic user interface that we don't have over here. We just need to construct the model in a paper and then get the coordinates and input the coordinates by hand. But aside from this, the core engine is identical to expensive structural analysis program. One thing, we are using just a simple solver. So if the problem gets really big, but I don't think that your truss is going to be that big just for 2D planar truss. So it will not be that big. But let me look up. If we can change the solver, then we'll fix it. But for now, it is just good enough for you to play around with this piece of code. All right. So that's it for today. I'll upload this video and you can check back again for the point that you cannot see easily. All right.